Okay, so many times I say that, teaching or learning is to do a lot of repetition. So this is again something that you probably seen in solid mechanics, which is the single slash double shear connection. Okay, so now that you are experts about normal stresses, shear stresses for combined learning, let's see now if we can do some design, let's say, some connections. Okay, so the single shear connection let's say single shear is basically the easiest one of them is you take two plates. So let's say it will be one. Let's say this will be another one here. Okay, and you're just going to connect them, let's say with a bolt or with a screw with a bolt, okay? All right, so remember here you can have, so basically that means that these are connected this way, you cannot pull them down, pull them to the side. If we look at one of the elements, either this one or the other one, if I do a little figure of this little segment over here, so let's say we take the top one, so that means the force is over here. Okay, so this bolt here will be subjected, if it breaks, moving in that direction will be breaking into what? Normal stresses or shear stresses? Shear, no? Okay, so what should be the equation for shear? Shear should be generally is what? Force, let's say shear force over area, no? All right, so here what is the value of the force is F over A. Okay, if you want, let's do this like the way we did it. I did it this way. This is the result, but let's say we do this like you were starting a beam. So let's say you start from this end over here, and then you make a cut, no? Okay, so in that case, that way you will see that V equal V basically. So this is your cut. Again, you don't need to do this. It's just to show that the procedures we do always work. We have the force, F, so we don't have the force. Here, distributed force F. Okay, so I'm just starting from the top, I make the cut. So here we apply summation of forces equal to 0. I keep forgetting the V over here. We want to make this one to the other direction. That way we get the positive sign, make it left. But basically we get the same equation. So from here you will see that what F minus shear force equal to 0, which means that the shear force should be equal to the force. And that's what's basically here we have that equation here, okay? But you see again that doing the procedure, making a cut, everything works. Oops, somebody admit here. Okay, so we're talking about the single shear connection. To do connections, this is the single shear. Okay, you like connecting two plates. The double shear. There's somebody that just joined. So the double shear connection. I'm looking at this a chat or something, but no. Okay, so double shear connection. This time is what do? We're gonna have basically three plates. Let's say this is one, then we're gonna get here. Another one, and let's say here do something similar to this one. So this time, again, we're gonna have a bolt that's gonna go all through the three plates. Okay, so here we need to be careful. So if we pull on this side with the force F, then that means that the force on this side, on each one of these plates will be what? Half of it, no? Half of it too, because we know that at the end, we need to be able to apply the equations of equilibrium. Okay, so if I do the free body diagram here, let's say of the bolt. Okay, so let's say this will be this line over here, this will be this line over here. So what are we gonna have over here? Oops. Yeah, move it. Okay. What are we gonna have over here? On the top section, that will be this one, we'll have here F divided by 2. We have the same thing on the lower one. And then on the middle one, we'll have the force F. This was before, if we follow the normal procedure, let's say we make a cut. So really, if we were just following a beam, how many cuts would you need in this beam over here? If we consider, if we assume the bolt to be as a day. So you have to do one here, yes, 2 cuts, no? So let's say we make the first one. That should be somewhere between this one and this connection. So in that case, we have here divided by 2. Let's say here, so the sign work fine. Let's say V goes to the right. Oh, let's just go back for 1 second here on top. Maybe I need to verify. What is A over here? Cross-section area. So that means that if I do a figure, is the basically this is the diameter of the bolt, is this area over here, no? Okay, so it's the cross-sectional area, as you said. All right. So basically, now we come over here, we do summation of forces equal to 0 as before. So what are you gonna have? Minus F over 2 plus V equal to 0, which means what? That the shear force is going to be on the force. So now, if I look at the shear, that will be on the board. What are you going over here? The 2 over 2A or V, sorry. Yeah, that's correct. V over 2, or you can write here V to A. Over to A, okay, which is. All right, so again, so this will be for shear connection. And this equation here will be for single shear. Okay, I'm pretty sure this is not new, no? Okay, so why am I doing this? Is because let's say now, and I always do this little example here. Okay, so we're going to look at a connection. So let's go here. Example. Okay, so let's write here for the below structure. Yeah, and what I do is only an L-shaped beam. I should have done it bigger. So this is what we have here. Yeah, let's do it that way. Okay, so let's say you have this beam over here. Let's say we put a value here of force of 1,000 newtons. Okay, and let's say the distance between these 2 points over here, so the center of this one, you understand why I put the center, let's say, is 10 meters. I put easy data. And here, the whole idea, the whole about this point is that let's say you have two beams, one vertical, one vertical, one lateral, and you want to put them together. So if you look at the buildings, what do they do? I mean, they do either or they do both, but let's say you decide to connect them with 4 bolts, no? A bolted connection. All right. So let's say you have these problems to do. You see, it doesn't look that complicated. But the question here is to determine, you do the design, and I'm asking you to determine the minimum diameter of the bolts. Okay, that should be a reasonable problem that really you should be able to do now, no? Okay, but again, we're going to do it again, repetition, no? All right. And again, I do like my approximation. I don't go in very big detail about the connection because I'm more interested about the understanding. Okay, so over here, we're going to make the first assumption, which is going to be what? So basically, in real life, what's going to happen if this force is too big is that this beam over here is going to bend, as this one also deflects, no? Okay, but if we want to keep it simple, what is something we can do? Because otherwise we need to look at the information. Let's assume that this beam over here is fixed here at the connection. Okay, so let's assume horizontal beam is fixed connection. What does that mean? That just means that if I do this one here, you see I could take this one as being fixed. And now I can just consider, let's say this is a force, F equal to 1000. And let's say assume that this is exactly at the 10 meters, okay, at the middle. So let's say it's 10 meters. Okay, so now that you are experts, maybe I'm going to skip some details. Let's say we first look at the loading. So again, you can do the reactions, whatever you want, but let's say we look at the shear. So 0, let's say to 10. Zero to 10. So let's say this is the shear, this is the moment. Okay, should be pretty simple. Or here for you to find. All right, so what is the shear along the full beam? It will be a constant value, no? You're absolutely correct, of V equal to 1000 newtons. What will be for the moment? And also at the end should be 0. And here what should be the value of the moment? Will be 1000 times 10, no? So will be M here bending moment, if you want, will be.
Why is the moment at 10 meters 0? That's not fixed.
I mean, if you do the equation, that's what you find, okay? But you want to know why is 0 here?
Yeah.
Okay, so let's put it this way. Let's just use by common sense. Otherwise, I could tell you using the equations, but if you're holding something like this way, just on one hand, and you push down, okay? This which end is resisting the moment? This one, no? This one is completely free, no? But this will still be the same though, if you are here, let's say with support. No? This is still free to rotate about this point, no? Does that make sense or no?
Yes.
Okay. Well, this is 10,000. Yes, so basically I did for the whole thing, but let's say, so at connection, maybe I could do that on the next page, but it doesn't matter. So at connections, at connection, which is the fixed end, what do we have? Shear force will be 1000 newtons, and the moment will be 10,000 Newton meters. Okay, the next step is generally where you get a bit lost. All right. This will be the loading. So now we're going to go at the connection. I'm going to do a little figure, a little diagram. Again, this is assumptions, but let's say This is completely random. Okay, let's say, so what would be the middle? Let's say this will be the middle. Okay, so just for simplicity, let's say this is, I mean, that's maybe a lot, but it doesn't matter. I mean, it's just dimensions. That might be, I mean, the beams are big. It's not unreasonable. Let's say this will be a 0.5 meter. Okay, so this is a square. This will be, a distance not that important, but let's say this will also be 0.5 meter. And now what's important is that let's say I'm going to put one bolt over here and another one over here, over here, and another one over here. Okay, so that in this case, we're going to measure that, let's say the center from this bolt to the center to this bolt. Is 0.2 meters. And that from the center of this bolt to the center of this bolt will also be 0.2 meters. Okay, so if I simplify a lot everything, what will be the loadings in this cross section? Let's say we'll have here shear force V, and we'll have here the bending moment M. Okay, so the bolts over here will be breaking due to what? We just did it before, the bolts will break due to shear, no? So what is shear? It's force over area. So what will be the value of the force?
V.
V, that's it? All right, I don't, this on the figure here is V. We look at this V. So then the moment is not doing anything? Huh?
It's doing something.
This is doing something, no? Okay, but what is it doing? That's the whole thing, no? Correct. So basically, the total shear that the ball is going to have to resist this is the normal shear force plus the shear force that is produced by the bending moment. Okay, so we can start here. V total will be equal to V plus, let's call this one V sub M, where V sub M, let's say, will be shear induced bending moment M. Okay. We find Vm. Okay, so let's say Vm is not complicated at all. It's a definition of a moment. Okay, so it's everyone is R cross F. That's the correct, the very detailed definition. But we could say in general is what is just force into the multiplied by the no. Okay, so over here, the force we're trying to find is Vm, because the moment we know is 10,000. So basically, we're looking at a Vm over here. And what will be the arm? The arm should be then, I don't know how much it is, but it should be the distance between the center here, let's say, O, and the center of the ball, no? So that distance here, from here to here, We have here D, 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 and D as well here, no? Those 4 different Ds. Force times D. D is the distance between point O and the center of the bolt. So then D will be equal to what? Will be square root of what? Of will be 0.1 square now, correct? Plus 0.1 square. Which if you do the calculation, I think I have it here is equal to 0.14142. Okay. You want to go and double check because what I do most of the time, I change my data every single semester. Okay. I do this once with you in class. All right, so if we have this, then this will mean that the shear force induced by the moment will be equal to the moment divided by D, which will be 10,000 divided by the 0.14142. And this gives 70.7106 10 to the 3 Newton. Okay, so the next assumption that I want to do over here, I want to write it down and then we're going to discuss it, okay? So if every bolt carries the same load. Is that a reasonable assumption for you? Yes.
Do we know which direction the V due to the moment is acting?
Okay, let's put this. The way I do this one, Johnny, if you have a force, when I do structure, I like to think about external, internal, correct? So, or if you want like third Newton's law, action, reaction, no? So if you push down the structure there is going to try to do what? To push in the opposite direction. Okay. But even if you have the sign at the end of the day is not that important here, no?
Okay.
But I mean, that's the way I do it in my head.
Okay. I was just wondering.
Yeah. Same thing for the moments. If you look at the moment really is going in that direction. So really at the connection, I do the moment on the opposite direction. And this will happen generally when you do the, if you do the loading, then you find the reaction and you start doing the cuts, that's what you're going to find. Yes.
For this problem, are we looking at reaction forces or internal forces?
We're looking at internal forces. But in this case, it will be the same as the reaction forces because we are looking at the row. Okay. Yeah. So again, I'm going to do a discussion here, okay? Because of the assumption, because I want you to think that every single problem only has one solution. Okay. So for example, here when we did the movement, we took it from the end to the middle of the connection. Okay. If we wanted to be a little bit more pessimistic, what could we have done? We could maybe take it from the end all the way to the left-hand side of the connection. No? Yeah. Okay. Another thing, is it really the same moment, or should it really be the same moment being applied to each one of the rows? No, okay. But to simplify everything, what did I do here? I just assuming that it's going to the middle. I can distribute it evenly among all the rows. No? Okay. Now, another assumption here. Johnny, this one is not that good. Okay. If every box carries the same loading. So that basically means that whatever we're going to divide it by 4. Okay, but what happens if one of the bolts break? I mean, you should maybe do the design, let's say in your head, maybe, I mean, how many bolts do you need in order for this not to rotate? Minimum. 2, no? Okay, so maybe a better assumption will be, okay, let's assume that 2 should be sufficient to carry the full load, no? And the other one will be as a factor of safety. Okay, so you see there is different design considerations that you can do in this problem, no? Yes.
Would it be safest, like, would it be a good practice if we just took the moment all the way from the left end and then assumed all 4 were the same loading?
I will do that as a factor of safety. Like I said, initially I will always do that. It's safer, and then if you need to reduce weight is when you start doing more accurate stuff, okay?
I'm just thinking that if your 2 bolts on the left-hand side are sufficient enough, then the one on the right should be good enough.
Correct. Yeah, I mean, that's a perfect assumption. Okay, but that's what I'm trying to say. It's not like one solution to the problem, no? All right, everybody may have slightly different solution, but this is the assumption that I'm doing here. So if every bolt carries the same loading, then what does that mean? That then I'm going to put it here. Maybe it will be easier. V carried by each one of the bolt will be the V total by 4. Okay, so V total will be equal to what? We say was equal to V plus V. So what was V? 1000 plus, here you see the big mistake that you do if you forget to add the shear force added by the moment, no? Is 70.7106 10 to the 3. Okay, so that's easy. This would be whatever, 71.7106 10 to the 3 newtons. And the shear seen on the ball would be V bolt, will be V total divided by 4. Which is 17,927.7 newtons. Okay, any questions so far? Does everything make sense? All right, so now the last thing we need to decide. All right, let's say another assumption here. So basically now, again, depends on how you design it. But in this case, maybe it's too simple. What type of connection do you think over here? Single or double?
Single.
Looks like the easiest one would be the single, no? In this case, all right? So let's say, assuming, so let's say 4 single shear connection. So again, what are you gonna have? If this is your bolt over here, all right, this is a cross-sectional area. So the cross-sectional area would be equal to what? In function of the diameter. Will be pi r squared, we could say will be pi D squared over 4. Okay, so single shear we know is tau equals the A. Basically, yeah, so this will be, and this is, be careful, this is B tau of the bolt. Let's say that the shear force that the bolt can resist, you go to the manufacturer page, you find that the maximum shear force that the bolt can resist is 15,000 kilonewtons per meter squared. So basically, if you go to a catalog with bolts, they will give you for which bolt, what is the maximum force you can resist in shear, and something here we don't do. And what is the other one they give you, Charlie? What do you think they should give you? This one, or what else? And the pull out, no? Because if you put here the bolt and you put here under the nut, it's also a certain force that you can pull up, no? Okay, and they find all those forces by doing what? Probably the STM test, no? Okay, so that's data you can find from tables. All right, okay, so I say this one is this. So in that case, what would I give you? So using the equation here, bolt equal V over A. So it will be V, how do we call that one? What's the page? V bolt. All right, so we have V bolt here divided by pi D squared over 4. So we can solve over here for D will be equal to what? Will be 4 V bolt. I'll move it to the top. Divided by pi tau of the bolt, and we take the square root of this one. Okay, and if we do the calculation, what I get over here is that D is equal to 0.039 meters, which is, so basically, obviously, you're not going to go out the catalog and find one that would be exactly your calculation, no? So you will go to whatever is higher, no? Okay, so let's say over here you round it off to 40 millimeters, okay? And you try to find now in your catalog one ball that will suit your design. Okay. Okay, so basically let's look a little bit back at this one, at this problem. So now let's say, for example, what I'm thinking about a plan to give you on the break, we can do it together, but maybe we can, if we have time today or next class, we design together. I could give you something like this, or let's say this is just bolted directly to the wall. I don't do this one, okay? And then put this over here, and then here going okay. Decide to put here on top of this one distributed loads. And then whatever. And let's say I decide here to make, because randomly I say, imagine that they don't find a beam that's standing around, you have 2 beams of 5 meters. Then you will have to connect them by putting some kind of splice that you need to put there, no? Okay. I can ask you, okay, assuming whatever, probably in this case will be more like a double shear, no? You will put one plate on each side, bolted all through it will be a double shear connection. Design the diameter of the bolts for, let's say, a safety factor. Let's say that the 2 bolts need to resist the loading for a safety factor of 2. So you need to do all the shear minimum and diagrams in order to find what? The load at this location, no? Yeah. So probably you can expect something like that for the break, no? So. All right. To the next big thing in this class, which is shaft design. Yeah. Okay, so what is a shaft? Anyone?
It's a metal rod used to convey rotation.
To rotate what type of energy?
To convey rotation.
Okay, but basically, you can instead of rotation energy, you can just say try to transfer power from one location to another one. Okay, but that's correct. So let's say, so a shaft, let's say, is a instead of a let's say is a mechanical, because we are mechanical, otherwise we call it structural, but it's a mechanical component. That transmits since you mentioned the term, let's use the term rotational motion. Added power, okay? We use exactly the words that we just defined. All right? I don't want anything complicated. Okay, so there is a reason why I introduced the term power, because that's the important one over here. What is power or a force for you? Yes.
It's a derivative of torque. It's
Okay, so all right.
some like divided by.
Okay, but what I'm trying to say is that okay, power, you agree that power is the same thing as work. Okay, to be correct. I know you know the first one. You are correct, okay, on what you're saying, but let's see if I ask you what is the work done by a force? What will be your answer? Force and distance, no? But that's for if an object is moving in translation, correct? Force and distance. So you mentioned what would be the equivalent for torque?
Rotations.
Rotation. So will be, but let's use the same semantic. You have force and distance. So for torque, the equivalent to force is what for torque? Moment. No? What do you use in static? Summation of forces and summation of moments, no? So summation of forces define the translational component. Summation of moments define the rotational, no? Motion. Okay? So force or moment will be equivalent to force. Now, what would be equivalent to distance for rotational motion? So you say work or power is equal force times distance, no? For summation of forces. So for the moments will be what? Moment times.
Rotations.
Okay, but what will be rotation? What rotation? The change in angle, no? What are the units? For power, if you do force times distance, is Newton's meters. Okay, you need to have the same units if you do that for the moments, no? If you do moment times angle, what will be the units? Force times distance as well, no? Yeah, because angle of units of angle are not considered, no? Right? So basically, what I'm trying to say is this, is that if you have a structure subjected to, let's say, a torque. Okay, so basically, so that would be the angle. So let's say power. Real definition is work over time. So what will be the work done by this one? We say will be T times d theta, no? And what will be, let's say this will be dt. What is d theta dt is equal to what? Omega, which is the angular velocity. So basically, at the end, we can say that the power of the shaft will be equal to what? T omega. Again, I don't think this is new. I mean, I don't know. Did you see that in solid mechanics, the basic problems? Okay. So basically, you will have P is power. And we have units of what? So let's say will be Newton meters per second, but that should be what? What should be the units of power? Watts, no? And this. Okay, then what do we have? T, I mean, T, you know, is the torque. In, let's say, Newton meters. And omega is the angular velocity that will be given to you in radians per second. Jan. Okay, so I'm going to give you this in case, because if I'm the one making up the problem, Jali, when you talk about frequencies, okay, angular velocities, do you talk about radians per second or do you talk about hertz? So I want to give the relation between angular velocity and hertz. So let's say using the relation is omega equals to 2 pi s. Then what does that mean? Something that you have P equals T omega equals or 2 pi F times T. F is the frequency in hertz. What is 1 hertz? 1 second. Okay, but now let's say really what does that mean? What is really the frequency? This is more vibration. Okay, so I'm not going to go into much detail, but there's something called a period. So what is the period now? Period is units of time. So what will be the period? The period is the time it will take for the shaft to go from this point, from any point. But let's say to go from this point to this point. That's the period. No? If you take 1, so the frequency basically is 1 over the period. Okay, where this will be times to go from point A go to point A. Right? That's why I want to go average. I want you to have some understanding. So far. So now you see that the load over here is not static anymore. It's due to the motion, no? To the angular velocity. Okay. So basically now, if we know that you need to design a machine for a certain, if you want to have a certain torque, a certain velocity, that's going to require a certain power of the machine, no? Of the engine, if you want, in order to rotate yourself. Okay. Or vice versa, if you want to have a certain power, the power will then depend on the value of the torque and the angular velocity. Okay. All right. So what I'm going to define now is the basic equation for the shaft design. So before that, let's just remember something. What was the definition of shear stress due to torque? TR over J, no? Okay. And this is subjected to a torque, okay? This is shear due to the torque. Okay, so I want to do here, let's say, basic, or instead of basic, let me just call them initial. Shaft design. Equations. Okay, so we have derived two equations. So far, we have derived one that is power equals to what? Torque times angular velocity. And the other one is shear equals to torque or torsion times R divided by J. Okay, J over here, I'm going to ask you one thing. In some books, is what they call I sub P, the polar relation. But I will call it J. So if I combine these two equations, a simple equation design could be what? The shear will be equal to what? What would be T? Power over angular velocity times R over J. Okay, but this is better understood if I write down over here, let's say, if I write this J, where I move it to the other side, would be equal to power over angular velocity times the shear. So basically, why do you think I divide this in these two parts? Yeah, I mean, but the left side, basically, these quantities are just related to what? It's just geometrical. Right, and really the J, we know what it is. Now pi over 32 will be radius to the cube, no? To the fourth. Okay, so we divide now by R, will be to the cube. But again, I put this one because we might use a shaft, we might use a tube, we might use different options, no? But this is basically based to geometrical consideration. Now, P W is related to what? P and W will be related to what? Loading, no? and maybe tau over here will depend on what? On the material use, no? Yeah, and let's say material for tau. So loading will be PW, and let's say material would be the tau. Yes.
The same on far
Right?
corner of the top of the page.
Well, I think. Yeah. So what there's something here that people do generally a design mistake, and I've seen that many times even here in competitions, okay? But let's say using the above equation, an engineer can determine the, let's say, the radius a shaft to, let's say, transmit the power P at a specified angular velocity omega. Okay, I'm going to add here if you want for a given material. Okay. So generally on a shaft, what will be attached to the shaft? I think we kind of give a brief introduction last time. Okay, it's going to rotate, but if now you want to transmit that to another mechanical component, generally that will be done with what? With gears, no? Okay, but when you use gears on a shaft, or really anything that's going to be attached to the shaft, what is something that maybe people are ignoring too much? What is something important? Okay, here we design, this is going to resist it in shear stress, no? Okay, we're going to find this is not going to break to shear stress, but what is something important, very important when you transmit power as well, when you have gears? Gear ratio, correct, but that's a different story. Basically, what I'm trying to say is that, okay, is that the shaft does not deform. In other words, you're not going to have any deformation, any change of angle when you have the connection of the two gears, no? Yeah, so basically, the angle of twist of the shaft, because you can have a shaft, and I think if you look at the equation, you use this equation, you're actually going to find that the most efficient shaft is not going to be a solid shaft, it's going to be a tube. Okay? Because the tube is the one who's going to have the highest J, okay? But you can do those calculations later. However, why do you use a shaft? Because now when you specify the shaft, then you're going to be able to have a much smaller angle of twist, no? Yeah? Okay? So let's argue that. So let's say something you must do. Okay, so a mistake that many people do, let's say over here, let me do this. Is that this one over here, which is a tube, that one has large J, but poor in angle of twist. However, a shaft, if you want has a lower J, but will be what? Good in angle of twist. Okay, what is the definition for the angle of twist? Is the equation is D. They use d theta or d phi. Let's use d theta since I use that one. D theta dx. Then it would be equal to T over GJ. So this will give you Johnny the equation that d theta equal to T over GJ dx. Again, Johnny, I'll just give the equation, but in this case, so if you integrate this one, say between 0 and the length, between 0 and and the last angle. So let's call it maybe phi, this one here, it's fine. And it will be between 0 and n. You find that the angle of twist phi will be equal to what? T over dj. And then I know from first hand that here at school when twice when they do the shot design for the marathon, they only use the top one. Then they go on competition. They have a lot of slippage on the gear, no? Because they're not completely attached. And due to the too much slippage, at the end, what happens is that the gears actually break due to the tooth, no? Okay, so this is something very important for you to check.
Is that 0 to phi for the first one?
Yes, you have to, yeah, change. Okay, so for today, I'm going to stop over here.